Imagine waking up one morning and discovering that everything you have ever known, your favorite mountains, your favorite memories, even that one embarrassing moment you pretend never happened, might all be the cosmic equivalent of a movie projected on a screen you can never quite see. It is a strange thought, like the universe suddenly tapping you on the shoulder and whispering, "Hey, what if I am not what you think I am?" And the wild part is that this is not just late-night dorm room speculation. Some physicists, people who use chalkboards as weapons and consider mild existential crisis a normal workday, actually entertain the possibility that our entire universe could be a projection from a higher dimensional reality. Not a glitch, not a simulation, but a projection, like something deeper and more complex is casting a grand cosmic shadow, and we are living inside it. Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing, but only if you enjoy these calm journeys through the universe. Now let's begin. This idea is unsettling in the best way, the kind of unsettling that makes you want to sit down with a cup of tea and question everything from the nature of space to why socks disappear in the laundry. Because if the universe is a projection, then the physical world is not the whole story. It is more like the cover page of a much thicker, multi-dimensional novel, one that we cannot open but are absolutely living in. And that thought alone is enough to make your brain do the scientific version of a somersault. Graceful in intention, questionable in execution. Now, do not worry. Just because the universe might be a projection does not mean you are about to fade away like a character who just found out they are fictional. You still get hungry, you still trip over your own shoelaces, and gravity still insists on doing its job even when you wish it would take the day off. But the idea that everything we experience could actually come from something happening in a higher dimension adds a layer of cosmic drama to our daily lives. Suddenly, walking the dog becomes a scene in a grander dimensional production you did not realize you were part of. If the universe had a director, you would definitely be in the cast, and no one even asked you to audition. Think about shadows for a moment. When you hold your hand near a light, the shadow on the wall is real in a sense. It has a shape, it moves when you move, and if you spend too much time making finger puppets, you might question your own maturity. But it is not the full version of what created it. It is a simplified slice of a more complex object. Now imagine the same idea on a cosmic scale. What if our universe is the shadow and the higher dimension is the hand? Somewhere, something incredibly complex could be shaping the reality we experience, but all we ever see is the simplified version, the shadow on the cosmic wall. And yes, that means the universe may literally be doing a giant version of the flashlight and hand trick, except instead of making bunny ears, it is making galaxies, stars, planets, and your neighbor who insists on mowing the lawn at dawn. The unsettling charm of this idea is how it reframes our place in the cosmos. Humans have always wanted to know what is really going on out there. We have stared at the sky, poked at physics, built telescopes that could probably read the nutrition label on a star if we really wanted them to, and still we cannot be entirely sure what the universe is. And the projection idea does not make things simpler. If anything, it adds a plot twist that feels almost mischievous. It is as if the universe shrugged and said, "Oh, you thought I was three-dimensional? That is adorable." But here's the fun part. The more we learn about the universe, the weirder it gets in ways that actually make the projection idea feel not completely ridiculous. Space behaves like it is hiding secrets. Information behaves like it is being stored in unexpected places. And reality itself occasionally acts like a magician performing a trick and daring you to figure out how it works. The universe seems to enjoy being mysterious. It is that friend who tells a story but leaves out the important details, and you cannot decide whether to be annoyed or impressed. And while the idea might sound bizarre, it also stirs a sense of wonder that feels almost childlike. To think that we could be living inside a grand projection means the universe is more than just distances, atoms, and the frustrating fact that your phone battery never reaches the percentage it claims. It suggests that reality might be woven from something richer, something smarter, something far more intricate than anything we can see. The universe might not just be big. It might be multi-layered, like a cosmic lasagna baked in a dimension we cannot enter. So this chapter begins with a question that will echo throughout everything that follows. What if reality is not the complete, self-contained thing we assume it is? What if we are only seeing the visible layer of something far deeper? What if we are living inside the shadow of a higher dimension that quietly shapes our world without ever revealing itself directly? It is a possibility that turns the entire universe into a mystery box we are only just beginning to pry open. And the best part is, no matter how strange it gets, the journey promises to be unforgettable. After all, you are about to explore the possibility that everything, space, matter, time, even your own existence, is part of a projection cast by something unimaginably grand. And that is one cosmic plot twist worth sticking around for. Try to imagine explaining the world to a creature that lives in a world flatter than your last cup of soda. Picture a tiny being living on a perfectly thin sheet, so thin that it makes paper look bulky. This creature can move forward and backward, left and right, but the idea of up is as impossible to grasp as trying to bite your own elbow. If you lift your hand above its world, it will never see it. To that creature, your hand does not exist until it touches the sheet, and even then, it only appears as a strange shape sliding around like a ghost that refuses to follow local zoning laws. This is the magic of dimensions. They are not mystical labels, but descriptions of the ways existence can stretch, move, and take form. Most of us stroll through 3 dimensions every day without noticing how impressive that is. You can walk across a room, step over a sneaker you swore you put away last night, and jump into the air, hopefully intentionally, and all of that is normal. But the moment you add a 4th spatial dimension, things get as weird as a cat's nightly routine. A 4-dimensional creature would not just move through space the way we do. It would have an extra direction available, a direction we cannot see or point to because our brains evolved to navigate the 3-dimensional world of predators, berries, and questionable cave decisions. We are built for this dimension set, not the next one. But even though our senses are locked into three-dimensional thinking, higher dimensions are not impossible. They are just invisible to us the same way a song is invisible to someone who has never heard music. To understand this, imagine holding a cube. If you could summon a cube into the world of that flat sheet creature, it would not see a cube. It would see a square that suddenly appeared from nowhere. Then it would watch in utter panic as that square changed shape, growing, shrinking, stretching, as the solid cube passed through its two-dimensional universe. You would not be performing a magic trick. You would just be moving the cube normally. But to the sheet creature, you would look like some kind of all-powerful shape-shifting overlord. That is the power of higher dimensions. From the outside, they make everything inside look incomplete. Our own world might be the equivalent of that flat sheet. We assume three dimensions are all there is because we live inside them, the same way a fish might assume the entire universe is wet. But physics does not care about our assumptions. There are theories suggesting that space could have hidden dimensions folded tighter than your favorite blanket at the back of your closet. These dimensions could be so compact and curled up that even a particle zipping around at incredible speeds would never slip into them. They would be like tiny cosmic hallways we cannot enter, but that still exist, shaping the universe quietly from behind the scenes. To get a feel for this, pretend your bedroom floor is the entire universe. You can walk north, south, east, or west. Now imagine that, in addition to those directions, the floor has a secret layer curled up beneath each floorboard. You cannot step into it. You cannot crawl into it, but it is still there, influencing how the room feels, how sound travels, even how gravity tugs at your toes. That hidden layer does not need your permission to exist. You just never notice it because you are not built to explore it, much like how you will never discover good life decisions hiding in the junk drawer. One of the strangest things about higher dimensions is how they could make sense of things that look bizarre in our familiar three-dimensional perspective. For instance, a four-dimensional shape, let us call it a hypercube because scientists love names that sound intimidating, could pass through our world and appear as an object that shifts shape right before our eyes. One moment it looks like a cube. Then it becomes a weird, stretched cube. Then it becomes something else entirely before disappearing. To us, it would look impossible, like geometry having a midlife crisis. The real challenge is that higher dimensions work the same way color works for someone who has lived their whole life seeing only shades of gray. You can describe it, compare it, gesture wildly while explaining it, but until they experience it directly, the concept never fully lands. We are creatures designed to grasp height, width, and depth. Add a new direction, one we cannot see, touch, or travel through, and our brains respond with the mental equivalent of shrugging. And yet, the possibility of higher dimensions is more than a thought experiment. It forces us to confront just how small our perspective really is. Even though we walk around feeling like we understand our world, we might be living in a tiny slice of something far more elaborate. If a higher dimensional reality is out there, then we are the shadow puppets, not the puppeteer. And somewhere, just beyond our senses, space could be stretching in ways we cannot visualize, turning corners we cannot follow, and hiding layers we cannot peel back. But that is the beauty of dimensions. They remind us that the universe is bigger, stranger, and more flexible than the cozy three-dimensional bubble we call home. And if higher dimensions do exist, they are not just extra directions, they are extra possibilities waiting quietly in the fabric of reality for us to discover them. If you have ever made shadow puppets against a wall, you already understand the basic idea behind lower dimensional shadows. You hold your hands up to a lamp, bend your fingers, wiggle your thumbs, and suddenly the wall displays the world's most questionable rabbit impression. The shadow looks real enough, but it only shows part of the truth. It is a flattened version of something more detailed. It has no skin texture, no wrinkles, no fingernails, and absolutely no clue that it owes its entire existence to your real three-dimensional hands. A shadow never knows it is a shadow. It just goes about its flickering business, unaware that its world is missing a dimension. Now imagine this idea scaled up from your living room wall to the entire cosmos. Instead of a lamp, think of a higher dimensional source. Instead of your hands, think of an object from a four-dimensional world, a world with an extra spatial direction we cannot point to, no matter how aggressively we gesture. If that four-dimensional object cast a projection into our three-dimensional space, what we would see might be just as limited as a shadow rabbit missing half its features. Our reality, in that sense, could be the cosmic equivalent of a silhouette, recognizable, functional, but missing the deeper structure that exists in the higher dimensional original. To get a better feel for this, picture a three-dimensional object casting a two-dimensional shadow. Take a teapot, for example, because nothing screams elegance like boiling water in a curved metal container shaped like a confused bird. Hold that teapot in front of a light. Its shadow on the wall might look like a squat blob with a handle sticking out dramatically, completely failing to capture the teapot's internal structure. The shadow does not show the hollowness inside where water sloshes around. It does not show the lid, the spout thickness, or the tiny chip you got when you dropped it that one time and pretended you absolutely meant to do that. Yet the shadow still responds to the real teapot. Rotate the teapot, and the shadow morphs instantly, stretching and shrinking like it is trying out yoga poses it is absolutely not prepared for. The shadow's existence depends entirely on a reality it cannot perceive. And as strange as it sounds, if our universe is a lower dimensional projection, we might be in the same position, changing and evolving in response to something deeper that we can never see directly. But the fun part is imagining how weird things would look if a four-dimensional object passed through our world. Suppose a four-dimensional creature decides to drop by the local grocery store, not because it needs food, but because it finds our three-dimensional produce section amusing. As it enters our world, you would not see the full creature. You would see a slice of it, the way a shadow is a slice of a hand. The creature might appear suddenly as a floating shape, change form in ways that ignore all known laws of common sense, and then disappear as if it simply forgot to exist. It would look less like a visitor and more like a glitching prop from a science fiction show. with a very confused special effects department. For another example, imagine a four-dimensional sphere drifting through our three-dimensional world. We would see it begin as a single point that suddenly pops into existence like an uninvited thought. As the sphere continues drifting through our space, that point would expand into a growing ball. The ball would reach its maximum size when the thickest part of the four-dimensional sphere passes through, and then it would shrink back down to a point before vanishing completely. It would look like a cosmic breathing exercise. Inhale, exhale, disappear. And just like that, the four-dimensional visitor is gone, leaving behind a very bewildered audience. Shadows also reveal something important. They lose information. A shadow tells you the outline of an object, but leaves out all the juicy details. If our universe is a projection from a higher dimension, we may be living inside a version of reality that is missing fundamental pieces. It is like trying to watch a movie, but only being allowed to see the silhouettes of the characters. You could follow the story, but you would miss all the subtle expressions, the background details. The fact that one character keeps wearing socks with flamingos on them. All of that is lost in translation. This missing information idea becomes even more fun when you think about motion. If a three-dimensional object moves in ways a two-dimensional shadow cannot predict, the shadow might behave in ways that seem bizarre from its own perspective. A circle's shadow might suddenly split in two, merge again, stretch into a line, or break apart entirely, depending on how the original three-dimensional object rotates or bends. If our universe is the shadow, then some of the odd behavior we see, not repeating anything from other chapters, of course, might be reality responding to higher dimensional motion. To us, the universe occasionally feels quirky. To a higher dimensional observer, it might just be stretching its limbs. There is also a playful philosophical twist here. A shadow does not know what it is missing. To a shadow, its world is complete. It does not wake up thinking, "Gosh, I sure wish I had a third dimension today." It simply exists with the dimensions it has. Likewise, we go about our lives assuming that three dimensions of space are all there is. We are the cosmic shadow puppets, feeling complete while not realizing how much richer things might be beyond our perception. Not in a sad way, more in the way a goldfish feels very proud of its bowl, without realizing it is in the middle of your kitchen counter. And that is what makes the idea of dimensional shadows so captivating. They challenge the notion that our world is the full picture. If a shadow can look real but be incomplete, then maybe our universe is real but also incomplete. Not broken, not lacking, just one slice of something grander. And somewhere, in a place we cannot see, the higher dimensional original may be shaping our reality in ways as natural to it as moving your hand is to you. That possibility turns ordinary space into something mysterious and wonderfully strange. Shadows are no longer just cute hand puppets. They are clues, hints, glimpses of how reality might work on levels we have never experienced. And the more we think about it, the more it feels like the universe might be holding up its own unseen hand. casting our entire existence as the most elaborate shadow show ever performed. If you have ever held one of those shiny, slightly suspicious stickers on the back of a notebook or a credit card, the kind that glints like it is trying to flirt with the nearest light source, you have already met a hologram. These little patches of rainbow shimmer look like someone trapped a tiny science experiment inside a piece of foil. But behind that shimmer is a surprisingly profound idea. A flat surface can store an entire three-dimensional image, not a sketch, not a drawing, but the whole depth-filled thing. It is like taking a full sculpture and convincing it to squeeze itself into a two-dimensional postcard without losing its personality. To get a feel for what makes holograms so special, think about regular photographs first. A normal picture captures the brightness and color of light bouncing off objects. If you take a picture of your cat sitting on a windowsill judging you, the camera records the light coming directly from that scene. It does not record the angles of the light or the way the light waves interact with each other. That is why a photo of your cat looks flat. You can see the shape, but you cannot peek around the cat's ear or look at how the whiskers curve in space. The photo cannot sneak in information it did not capture. A hologram, on the other hand, is a different creature entirely. It does not just capture light. It captures the way light waves overlap, interfere, and dance together. Think of it like recording not just the sound of a drum, but how the echo bounces off every wall in the room. The hologram stores those complicated wave patterns in a flat surface, and when you shine a light through it, the light reconstructs the original three-dimensional scene. It is like the universe's most impressive magic trick, 3 dimensions hiding inside 2. Here is an everyday analogy. Imagine listening to someone describe a cake. They can tell you it is round, chocolate, and topped with frosting thick enough to violate several dessert laws. That is like a normal photograph. It captures only surface descriptions, but a hologram is like actually having the recipe encoded into a sheet of paper. With the right tools, you could reconstruct the entire cake, not a drawing of it, but the whole layered, textured masterpiece. The hologram is not a picture of what the cake looks like. It is a set of instructions for rebuilding how light bounced off the cake from every angle. Now take something even simpler, shining a flashlight on a coin. The light bounces off the surface of the coin in complicated ways. Some beams bounce straight back, others bounce off at slight angles. Some highlight the tiny grooves on the edges. All of that chaotic reflection carries information about the coin's texture, depth, and shape. A hologram captures that chaos. It grabs all the overlapping waves and freezes them into a pattern that looks like abstract noise until the right light passes through it. Then, almost rudely, the pattern springs back to life in 3 dimensions. What is even stranger, and frankly quite rude on the part of physics, is what happens when you break a hologram. If you cut a regular photograph in half, you get exactly half the picture. Half a mountain, half a face, half a cat mid-judgment. But if you cut a hologram in half, each half still contains the entire 3-dimensional image, just with less clarity. It is like cutting a cake, but discovering each slice somehow still contains the entire cake. Your brain might protest, but the hologram does not care. Because the hologram stores information everywhere in its pattern, any piece of it still contains the whole scene. This property hints at something important. Holograms do not store images by location. They store images through interference patterns, which are spread throughout the entire surface. It is like writing a secret message not by arranging letters, but by creating ripples in a pond. Every ripple interacts with every other ripple. Remove part of the pond, and the remaining water still holds the pattern of ripples, just fewer of them. The message is weaker, but not lost. This idea alone would be enough to make holograms feel like a strange party trick of physics. But what makes them truly fascinating is how they hold deep information on flat surfaces. A hologram can store the illusion of depth, curvature, and structure, even though it is nothing more than a thin film. And this is where our imaginations start taking off on cosmic tangents. Because if a little shimmering sticker can hold the blueprint for a three-dimensional object, then flat surfaces might not be as simple as they look. They might be hiding detailed patterns that create an entire spatial scene. Think about it as a form of compression. If a sheet of film can hold an entire three-dimensional image, then a surface might carry far more information than its appearance suggests. Suddenly, flatness is not a limitation. It is a storage strategy, a cleverly organized one. A surface might hold the full story of an object, waiting patiently for the right light to reveal it. To make the idea even more down to earth, imagine drawing a maze on a sheet of paper. It looks flat, simple, manageable. But now imagine that the maze secretly encodes instructions for building a full-scale labyrinth complete with walls, tunnels, secret rooms, and questionable design choices. The drawing looks simple, but a hidden pattern contains everything needed to reconstruct the full three-dimensional structure. A hologram works much the same way, except instead of tunnels and rooms, it captures and rebuilds light itself. You can think of the flat hologram as a kind of map for how light should behave to recreate a full three-dimensional scene. When light hits the pattern, it follows those instructions and rebuilds depth from a surface that technically has none. It is one of those moments where physics leans in and whispers, "Dimensions can be tricked." And that cunning trick, storing complex, volumetric information on a flat boundary, is what makes holograms so astonishing. A surface can hold more than meets the eye. It can hide depth inside flatness. It can turn two dimensions into three through patterns that look meaningless until the right illumination reveals their secret. If a small hologram can do that much, imagine what a cosmic hologram could hide. But that is a mystery for another chapter. Imagine walking into a museum where the walls seem suspiciously blank. No paintings, no sculptures, not even a gift shop mug with a questionable pun. Yet somehow, the tour guide insists that every detail of the museum, every artifact, every exhibit, every ancient coin somebody definitely pocketed centuries ago is stored on those very walls. The walls do not display it, they contain it. The entire three-dimensional history of everything in the museum is encoded on a two-dimensional surface, like the universe's most cryptic scrapbook. That strange idea is at the heart of what physicists call the holographic principle, the notion that all the information in our vast universe might actually live on a boundary surrounding it. To break it down, Imagine the universe as a giant cosmic theater. We are sitting inside, watching the show, feeling like we are part of the action. But what if the script, the props, the cast list, and every possible plot twist are not stored within the theater at all? What if they are written on the walls outside the stage? That would mean everything we experience, including the space we move through, the atoms making up our cereal bowls, and the dramatic sigh you give when you drop something under the couch, is actually emerging from information imprinted on a distant surface we will never reach. It is like living inside a story written on the cover of a book rather than on its pages. The holographic principle gets its name from holograms, but not because the universe is a giant sticker pretending to be three-dimensional. Instead, the idea comes from how holograms work. They store the full three-dimensional image on a two-dimensional surface. They do not need depth to encode the illusion of depth. Likewise, the universe might not need its full volume to encode the information that builds everything inside of it. Space, in this view, is not the storage container. It is the result of the storage system. To make this less abstract, picture a massive cosmic bubble. On the outside of that bubble is a surface, thin, distant, unreachable. According to the holographic principle, that surface carries all the information needed to construct everything happening inside the bubble. Every galaxy, every star, every swirling cloud of gas that looks suspiciously like an interstellar noodle, all of it exists because information on the boundary is encoding it. And we, living deep inside the bubble, see the encoded information unfold as the reality around us. Now, this idea is not just philosophical musing, or the result of scientists drinking too much coffee and deciding reality needs a plot twist. It grew from a very serious question that physics struggled with for years. How does the universe store information? When scientists study objects like stars or planets, their information content, the details needed to describe them, scales with their volume. A bigger object holds more information because it occupies more space. Simple enough, but something strange happens when you look at areas where gravity becomes intense, such as in the regions surrounding extremely compact cosmic objects. In those places, the amount of stored information seems to depend not on the object's volume, but on its surface area. That was a huge surprise. It is like realizing you can fit the same amount of data onto the surface of a balloon as you can inside the entire balloon. You could scribble all the important details on the outside, and somehow that would be enough to build the entire inside. This revelation did not sit quietly. It whispered something game-changing. Maybe the universe does not store information the way we thought. Maybe surface area is the true storage space of reality. The holographic principle takes that hint and runs with it like a very excited dog discovering a new scent. It suggests that all the information describing our universe, the structure of space, the behavior of matter, the flow of time, might live on a cosmic boundary with 2 spatial dimensions instead of 3. That boundary does not have to be a physical wall or a glowing shield or anything dramatic. It can simply be the mathematical surface that surrounds the universe, and the universe itself, with all its vast space and depth, could be the 3-dimensional image that this boundary information generates. Imagine reading a comic book. The pages are flat, but your mind constructs a rich world with depth, setting, and movement. The holographic principle proposes something even more ambitious, that the universe might be, in a sense, reading itself from a boundary. Space could be the result of information unfolding from a surface, the same way a story unfolds as you move from panel to panel. Except instead of speech bubbles and dramatic sound effects, this cosmic story uses geometry, physics, and fields. One of the most astonishing parts of this idea is how it reframes space itself. We usually think of space as a giant container you can move through, like a cosmic warehouse with aisles and shelves. But the holographic principle suggests that space might be an emergent illusion, a byproduct of how information behaves on the boundary. In this view, space is not fundamental. It is a downstream effect, like steam rising from boiling water. The boundary is the pot. The universe is the steam. Even more wild is the idea that everything we think of as local, your ability to walk from your couch to the refrigerator in a straight line while pretending you totally forgot you just ate, is actually built from non-local information. The boundary's data might be stretching across cosmic distances, and we only experience the neat, orderly, three-dimensional result. The philosophical implications are mind-melting. If the holographic principle is correct, then we are not inside the universe in the way we imagine. We are inside the expression of information from a boundary. We are living in the three-dimensional projection of a two-dimensional informational blueprint. Not fake, not simulated, just encoded differently than we ever expected. And maybe the strangest part is how natural it begins to feel once you sit with it. Like finding out the universe keeps its diary on the walls of existence rather than in its heart. A little weird, a little wonderful, and full of secrets waiting to be decoded. Picture a library so mysterious, so obsessive about record keeping that it refuses to let a single detail slip through the cracks. A library where every book, every receipt, every forgotten shopping list, and every questionable doodle is cataloged perfectly. Now imagine that this library is not a building at all, but a cosmic beast with gravity so intense it bends the rules of reality the way a toddler bends rules about bedtime. That is essentially what a black hole is, the universe's most dramatic librarian, guarding information with an intensity that borders on cosmic paranoia. Black holes begin as massive stars that collapse under their own weight, squeezing themselves into an object so dense that space practically throws up its hands and says, "I give up." Their gravity becomes so strong that not even light can escape. Once light cannot escape, you know the universe is taking things seriously because light usually gets VIP access everywhere. The boundary around a black hole where escape becomes impossible is called the event horizon, a completely misleading name because it sounds like a fun sci-fi music festival. In reality, it is more like a one-way door with a very strict policy. You can enter, but you cannot leave, not even to complain about it. The strange thing about black holes is how they deal with information. When something falls into one, whether it is a star, a cloud of gas, or an astronaut who took a very wrong turn, the object does not simply vanish. At least, not according to the laws of physics. Those laws insist that information cannot be destroyed. You can shred it, scramble it, bake it into a casserole, but you cannot delete it entirely. So when objects plunge into a black hole and seem to disappear forever, a contradiction emerges. The universe claims information should survive, but the black hole looks suspiciously like it is eating it. For decades, this contradiction drove physicists up various walls. It became known as the information problem, which is honestly a polite name for something that made the scientific community collectively squint at reality. If information cannot be destroyed, then where does it go when the black hole swallows it? Does the universe smuggle it out the back? Does it hide it under the cosmic rug? Does it keep it in an interdimensional filing cabinet that no one wants to open because it definitely smells like old coffee? Everything changed when researchers began noticing a startling pattern. The amount of information a black hole can store, its capacity, so to speak, does not depend on how large it is on the inside. It depends only on the surface area of its event horizon. This is like being told that the size of your hard drive depends only on the dimensions of its outer casing, not on any internal components. It is as if the black hole said, "All my secrets go on the surface. Thank you very much," and refused to discuss the interior at all. And that strange preference for surface storage is not just a quirk, it is a rule. The bigger the surface of the event horizon, the more information the black hole can store. That means the skin of the black hole, the thin boundary where things cross into no return territory, is the librarian, the archives, the whole filing system. The inside may be terrifying and unknowable, but the surface is where the cosmic bookkeeping happens. Imagine tossing a book into a fire. The book burns, the pages crinkle, the text turns to ash. The information in that book seems gone forever. But now imagine that instead of burning, the fire pressed every single detail of the book's story onto its outer flame like a stamp. The book is gone, but the story is still written on the fire's surface. That is what black holes appear to do. When an object falls in, the details about that object, its properties, its history, its quantum fingerprints, get recorded on the event horizon. The object is gone, but its informational echo remains, clinging to the surface like a stubborn sticker. This was not just a neat discovery, it was a revelation. It told physicists something profound. Maybe information prefers surfaces. Maybe surfaces are where reality stores its deepest records. Black holes, then, are not just cosmic vacuum cleaners sucking up matter. They are vaults, keeping information in a thin layer wrapped tightly around their edges. It is almost poetic in the way that only deeply confusing physics can be poetic. Black holes also do something else that adds to the intrigue. They slowly evaporate over immense cosmic timescales, a process that can take longer than your average universe lasts. As they evaporate, they are believed to release the information encoded on their surfaces, not in neat formats, not with clear subtitles. More like the universe whispering the original details back into space in tiny fragments, like a librarian reluctantly returning overdue notes through a slot in the wall. It is messy, but it keeps the universe's promise. Information does not disappear. This surface-based information storage made scientists reconsider more than just black holes. If these cosmic monsters store information on their boundaries, maybe the universe does too. Maybe surfaces, not volumes, are the natural place for reality to keep its data. Black holes became examples, extreme, dramatic, slightly unhinged examples of how the universe might handle information everywhere. The more physicists studied black holes, the more they realized that these objects were not just destructive. They were teaching tools. They were shouting through their gravitational fields and stubborn refusal to obey easy logic. That information might live on boundaries. If the most extreme objects in the universe store their data on surfaces, perhaps the universe itself follows the same rule. Black holes. Those cosmic librarians with their intense seriousness pointed toward a new way to think about reality, that surfaces might be the true vaults of existence. And in that realization, the seeds of a much grander idea were planted. An idea where the universe itself, with all its depth and structure, might be the ultimate surface-encoded masterpiece. If someone told you that space, the vast cosmic stage where galaxies pirouette, planets tumble, and you occasionally trip over your own feet, might not be a fundamental thing at all, you would probably stare at them the way you stare at a microwave when it suddenly beeps for no reason. Yet that is exactly what some physicists suspect, that space is not a built-in feature of the universe, but something that forms from an underlying layer of quantum information. In other words, space might be less like a physical fabric and more like the universe's user interface. To get a grip on this idea, pretend your favorite video game world is real, not the characters or storylines, but the map itself, the mountains, forests, glowing crystals that definitely do not look suspicious at all. All of those landscapes look solid when you play, but behind the scenes, they are not actually objects. They are instructions, code, information. The game does not store a mountain. It stores data that tells the graphic system how to build a mountain when you look at it. If the universe works anything like that, then space might be built from information the moment it is needed, not something that exists independently. But do not picture space as a grid waiting patiently for instructions. Picture it more like a recipe that appears only when the ingredients come together. If two particles interact, they are not moving through space the way billiard balls roll across a table. Instead, their interactions could be stitching tiny pieces of space between them, sort of like two friends spontaneously knitting a scarf every time they make eye contact. The scarf is not made ahead of time. It appears because the relationship exists. At the center of this idea lies quantum information, the smallest, most stubborn form of knowledge the universe carries. Quantum information is not like the information in books or text messages or those long receipts that list every item you bought, plus several you definitely did not. Instead, it is woven into the relationships between things, the correlations, the patterns, the who is connected to whom of the quantum world. And those connections may be the true building blocks of space. To picture this, imagine a huge party where every guest represents a tiny unit of quantum information. The guests do not talk using words. Instead, they communicate through synchronized dance moves. If two guests are perfectly in sync, they become closer, not physically, but in the invisible layout of the party. If other guests fall out of sync, their distance increases. Before long, just by watching the patterns of who dances with whom, you could draw a map of the party. You could tell who is near, who is far, and who is on the opposite side pretending not to know anyone. That map emerges from the connections. No one placed the guests on a floor plan. The layout grew from the relationships. Some scientists think the universe works similarly. Tiny bits of quantum information form networks of relationships. And if we could zoom in far enough, far beyond atoms, beyond particles, beyond anything you can see even with a microscope that looks like it belongs in a science fiction medical drama, we might discover that space is not smooth at all. It could be a web of connections, like an invisible cosmic dance floor. And the geometry of space, the distances between things, the shape of regions, the curves of the cosmos, could be nothing more than the structure of that information web. Another way to picture this is with an enormous friendship chart. Imagine you map out the friendships in a giant social group. People with lots of mutual friends cluster together. People with no mutual friends drift to the edges, probably sipping soda and pretending they prefer solitude. If you draw lines showing every friendship link, the picture starts looking like a shape, clusters and gaps, close ties and far ties. You could take that diagram, erase all the names, and still see a sort of geography. That geography emerges from the connections, not from actual physical space. This friendship geometry is similar to what quantum information might be doing, creating the shape of space from patterns of connection. One of the weirdest consequences of this idea is that distance might not be what we think it is. We picture distance as a fixed thing. A yard is a yard, a mile is a mile. Unless you are jogging uphill and suddenly a mile becomes several emotional miles. But if space emerges from quantum information, then distance is determined by how much information is shared between 2 points. Two particles with strong quantum connections might be close, even if they appear far apart in normal space. This would make the layout of the universe less like a static map and more like a relationship graph constantly updating itself. And if the structure of space comes from quantum information, then space is not in charge. Information is. Information sets the rules, draws the boundaries, and tells particles how to move. Space just shows up afterward, like the backdrop of a play that has been built from the actors' interactions, rather than from any backstage carpentry. Now, this does not mean the universe is secretly a computer in the digital sense, but it does mean the universe might store reality in terms of relationships rather than locations. And that flips our intuition on its head. We like locations. They are comfortable. I am here makes sense. But if space emerges from underlying connections, the universe might be whispering, actually, you are not in space. You are in a network. This idea also gives space a kind of fragility, or maybe flexibility. If the connections rearrange, the shape of space could change. Not in a dramatic, your living room suddenly becomes a canyon way, but in a subtle, structural way that affects how the universe behaves on huge scales. In this picture, space is not a rigid stage. It is the choreography of countless quantum relationships moving together in silent coordination. And perhaps the strangest, most delightful part is that if space emerges from quantum information, then the universe is not a place you live inside. You are part of the information itself, the patterns, the connections, the structure. You are not in the cosmic dance. You are woven into it. If quantum information is the hidden recipe behind space, then entanglement is the stitching that keeps the whole cosmic quilt from falling apart like a badly sewn sweater. Entanglement is the universe's way of saying, these two things are connected. Do not ask how. Do not ask why. Just accept that they share secrets faster than you share gossip with your closest friend. In fact, if particles were people, the entangled ones would be the duo who finish each other's sentences despite living on opposite sides of town, in different time zones, with no cell service, yet still somehow manage to agree on everything instantly. At its core, entanglement is a relationship, a weird, clingy, unbreakable relationship. When two particles become entangled, their properties lock together, forming a bond so deep that you could separate them by enormous distances, and they would still act as if they were sitting in the same tiny chair. Change something about one, and the other responds instantly, as if the universe installed a private messaging app that works faster than any wireless provider ever has or ever will. Einstein famously called this spooky action at a distance, which is probably the closest science has ever come to shrugging and saying, "Look, we are all confused. Please bear with us." But what does this have to do with space being held together? Quite a lot, as it turns out. If you zoomed in on the universe far enough, far beyond atoms and their orbiting companions, far beyond subatomic particles doing their energetic jitterbug, you might find that the very structure of space is nothing more than an enormous web of entangled relationships. Imagine space not as a smooth sheet, but as a knitted fabric. Each stitch represents entanglement. Pull out enough stitches and suddenly the fabric frays, holes open, and eventually the whole thing unravels like your favorite sweater after one ill-fated encounter with a washing machine. That is the idea some physicists are exploring. Space stays intact because entanglement ties everything together. Without these quantum-level bonds, the universe would not just be empty. It might not have any meaningful shape at all. It would be like trying to sew a quilt using threads made of fog. Entanglement gives those threads strength, structure, and the ability to bind patches of reality to one another, keeping space coherent rather than crumbling into a heap of disconnected fragments. To picture this, imagine you are making a giant friendship bracelet, the kind made of braided threads that somehow always ends up too loose or too tight. Each thread represents a bit of quantum information. On their own, the threads are just loose strands, but twist them together, knot them in the right pattern, and suddenly you have something strong enough to wrap around a wrist. Entanglement is the knotting. Without the knots, the threads fall apart. With them, the bracelet becomes a single, connected object. Now scale this up to the size of the universe. Instead of threads, you have quantum states. Instead of knots, you have entanglement. And instead of creating a bracelet, you are creating the entire fabric of space. The more entanglement between regions of the universe, the more tightly woven space becomes. Break the entanglement, and the stitching comes undone. Space, it seems, needs a good sewing kit. In this view, distance is not just about physical separation. It is about how strongly two regions of the universe are entangled. Places with strong entanglement connections feel near to each other in the geometry of space, even if they sit far apart on a map. Meanwhile, places with weak entanglement connections drift farther apart in the geometry, even if they are physically close. It is a bit like discovering that your closest neighbors are not the people living next door, but the people you share the most memes with. One of the big surprises from this idea is that the shape of space might come entirely from patterns of entanglement. If you took all the entanglement out of the universe, not that anyone would recommend this, you would not be left with empty space. You would be left with no space at all, like deleting the stitching from a quilt and discovering you now have a pile of mismatched scraps instead of something cozy. Entanglement is not something that happens inside space. It is something that creates space. This idea gets even more delightful when you consider that entanglement is a bit dramatic. It refuses to be halfway linked. It is either fully committed or not interested. Particles either share the same fate or go about their business like strangers in a grocery store aisle. This all-or-nothing attitude turns out to be extremely useful for building a stable universe. Think of it as the universe hiring a team of dedicated relationship counselors whose job is to maintain cosmic unity across impossible distances. Even more entertaining is how entanglement treats secrecy. If you measure one entangled particle, you instantly know something about the other. Not because the particle sends messages, but because they share a combined identity. They are two halves of the same quantum handshake. It is as if the universe misplaced the boundary between them and decided to pretend it was never there in the first place. And that missing boundary is exactly the point. When particles share entanglement, they blur the lines that would normally separate regions of space. They stitch those regions together with invisible threads. So imagine the universe as a gigantic quilt, every square representing a patch of space. Entanglement forms the stitching between those squares. Remove the stitching and the quilt disintegrates. Strengthen the stitching and the quilt holds together, even under cosmic strain. The entire geometry of the quilt depends on how the stitching is arranged. That is what entanglement may be doing, giving space its shape, its coherence, its ability to exist as a connected whole. And that leads to the wonderfully bold idea that we do not live in space. We live inside a tapestry of entanglement. Space is the shadow of that stitching, the smooth texture created by countless quantum threads woven into something we experience as distance, direction, and shape. The universe might not be built from atoms arranged in space. It might be built from entanglement shaping the very possibility of space itself. In other words, the cosmos is not simply connected. It is stitched together, one quantum knot at a time. For most of human history, gravity has been that mysterious force we blamed whenever anything fell, slipped, toppled, or otherwise embarrassed us in public. You drop a sandwich? Gravity. you trip over an entirely visible step. Gravity. Your phone slides off the couch, even though you swear it was nowhere near the edge. Gravity, being rude again. It is easy to picture gravity as a kind of cosmic magnet pulling everything downward. But the more we learn about the universe, the more it starts looking like gravity might not be a force in the traditional sense at all. Instead, gravity might be the universe's way of balancing its information tabs, an emergent effect of cosmic bookkeeping rather than a fundamental tugging power. To get into this idea, imagine the universe as an accountant with a massive ledger. It is not counting dollars or coins, it is counting information, details about particles, fields, energy, and all the tiny subtleties that make reality behave the way it does. Every patch of the universe is like a page in this ledger, and the universe works hard to keep those pages consistent. If one page gets more information than another, the ledger has to adjust itself so everything stays in harmony. That adjustment, surprisingly, might be what we feel as gravity. Start with the idea that information is not just a passive record, but something that carries weight, literally. Not in the sense of, my backpack is heavy because it is full of information, although that is true for textbooks and mildly true for tax forms. Instead, the idea is that different regions of the universe can store different amounts of information, and the universe tries to distribute that information as smoothly as possible. When information becomes unevenly distributed, when one region has more microscopic details packed into it than another, the geometry of space shifts to accommodate the imbalance, and that shift is what we interpret as gravity. Imagine a mattress covered in tiny index cards. Each card represents a bit of information, and the mattress is the geometry of space. If one part of the mattress gets an enormous stack of cards, while the rest remains sparse, the mattress sinks. Not because something heavy is sitting there in a classical sense, but because the information load is thicker. If you were a tiny creature crawling on that mattress, you would slide toward the dip. You would call that sliding gravity, even though the true cause would be the mattress adjusting to carry extra information. This perspective flips the usual explanation. Instead of saying mass bends space and causes gravity, you reverse it. Mass is a region where information becomes densely encoded, and gravity is the universe reshaping space to keep the information ledger balanced. Gravity is not a force acting on things. It is the result of space adjusting to keep track of its informational content. One playful way to visualize this is to imagine the universe as a very strict librarian who insists every shelf must remain perfectly organized. When new books or information get added to one shelf, the librarian shuffles the shelves around, shifting them until everything fits neatly again. These shifts ripple outward, rearranging the entire library structure. Now shrink that idea down to the smallest scales and replace books with quantum information. The rearrangement is gravity, the bending, curving, and tilting of space to maintain informational order. From this angle, mass is not something that creates gravity. It is something that creates informational density. A star, a planet, even a simple rock, All of them contain enormous amounts of underlying information. The universe responds by adjusting the shape of space around them to account for that information, and the curvature we observe, the gentle pull we feel, the orbiting paths of planets. All of those are side effects of the cosmic bookkeeping process. You can also think of it in terms of effort. The universe is lazy in a very elegant, efficient way. It tries to arrange itself in the configuration that requires the least amount of informational fussing. If information spreads out evenly, space remains flat and calm. But if information piles up in one region, the universe has to bend space to keep the overall system in its simplest form. Gravity, then, becomes the universe's shortcut, a way to maintain order without rewriting its entire rulebook. This view of gravity is also deeply tied to the idea that space emerges from quantum connections. If space is nothing more than the pattern of relationships between bits of quantum information, then gravity is simply what happens when those relationships shift to accommodate heavier informational loads. Regions with dense connections tug on the surrounding network, pulling everything inward as the underlying structure reorganizes itself. Not because the region is heavy, but because it is informationally complex. To make this even clearer, picture a giant spider web. Every strand carries tension. If you tie a bunch of beads to one part of the web, that region becomes more complicated. The web stretches and warps to balance the load. If you are an ant walking across it, you feel that warp as a pull. Not because anything is pulling you intentionally, but because the web structure changed to accommodate the beads. That is gravity, the warping of the informational web, not a force reaching out to grab you. This reconception also explains why gravity interacts with everything: light, matter, energy, you name it. Everything carries information, so everything responds to changes in the informational structure. Gravity does not discriminate, it applies to everything, because everything participates in the cosmic bookkeeping system. Perhaps the most surprising part of this idea is how natural it begins to feel once you embrace it. Gravity stops being a mysterious, invisible glue and becomes a consequence of something far deeper, the universe's obsession with tracking its own information. It is not a fundamental force in the traditional sense. It is an emergent behavior, like a crowd shifting collectively when someone opens a door. No single person decides to move, but the whole system adjusts. So next time you drop something and it falls, you can blame it on more than gravity. You can say, with absolute cosmic flair, the universe is just balancing its information again. And you would not be wrong. The universe is keeping its ledger tidy, one falling coffee mug at a time. Time is one of those things we think we understand, until we actually stop and try to explain it. It feels simple at first glance. Things happen, then more things happen, and eventually you wonder where your entire afternoon went because you spent it reorganizing your sock drawer for reasons even you cannot explain. But what if time, the familiar forward march we rely on so heavily, is not the whole story? What if our timeline is just a thin strand pulled from a much thicker rope? A single thread woven from a richer temporal fabric that exists in higher dimensions? Imagine you are watching a movie on an old film reel. The frames pass one at a time, giving the illusion of motion. You see the beginning, the middle, the ending, all in order. But someone outside the projector booth does not have to watch the film that way. They can hold the entire reel in their hands, seeing every moment of the story at once. The hero entering the scene, the plot twist you did not see coming, and the final credits where you realize half the people involved share the same last name. You, sitting in the theater, only experience the film frame by frame, but the person holding the reel sees the whole timeline laid out in front of them. It is not that the frames are happening simultaneously. They just exist all at once from that larger perspective. Now imagine time as that reel and our experience as the single frame view. When we think of time, we think of a line, past, present, future. But a higher dimensional being or system might see time not as a line, but as a landscape. Instead of walking along a path, they could look down at an entire map. Our idea of before and after might just be the way three-dimensional creatures process a much richer structure. Time could be a direction we move through, but higher dimensions might contain extra directions in which time can also spread, twist, or deepen. To picture this, consider how a two-dimensional creature interprets a three-dimensional object. If you pass a three-dimensional apple through their flat world, they only see slices, a dot, then a growing shape, then a shrinking one, then nothing at all. They would think the apple changed over time, appearing and disappearing. But from your perspective in three dimensions, the apple is not changing at all. You are just moving it through their limited plane. Their timeline of events, appearance, growth, shrinkage, disappearance, is simply their way of experiencing a higher dimensional object. It is time as a sequence because they cannot see the whole structure at once. We may be doing the same thing with time. What we call moments might be slices of a larger temporal structure passing through our three-dimensional reality. We interpret these slices as change, motion, aging, causation, and all the other things time does to keep life interesting and occasionally inconvenient. But if time has extra dimensional thickness, then every moment we experience could be just one cross-section of something larger and more intricate. One playful way to grasp this is to think of time as a giant cosmic loaf of bread. We experience one slice at a time. Each slice is a moment. But the loaf as a whole exists simultaneously from a higher dimensional viewpoint. You could access earlier slices or later slices, not by traveling back or forward the way we understand, but by sliding through the loaf in a direction our minds cannot currently handle. And yes, if this means the universe is basically a bakery of moments, you are absolutely free to imagine the cosmos as a celestial kitchen run by a higher dimensional pastry chef. This idea also offers a new way to think about change. In our three-dimensional view, change is something that unfolds. Flowers bloom, people grow, stars ignite, memories form. But in a higher dimensional sense, maybe the entire bloom of the flower, from seed to wilted petal, already exists as one extended temporal sculpture. We just move through it the way a two-dimensional creature moves through an apple. Our sense of flow is not the universe evolving. It is our consciousness sliding along a coordinate we cannot fully understand. Another intriguing consequence is that time might not be uniform everywhere. If there are higher dimensional pathways that time can stretch into, then regions of the universe might experience time differently because they interact with different parts of that higher dimensional temporal structure. Our familiar ticking seconds could be the local rhythm of a much larger, more complex clock. In other regions of the universe, or in other layers of its dimensional structure, time might ripple, branch, or loop in patterns we cannot detect because we only perceive the thin slice directly in front of us. This does not mean higher dimensional beings would casually rewrite their past or fast forward through their future like someone skipping boring scenes in a movie. Instead, it means their experience of time might be richer, not faster or slower. They might perceive relationships between events the way we perceive relationships between points in space. They could look around in the temporal landscape, seeing how moments connect in ways that are invisible to those stuck in a single timeline. Think of how you can see an entire map at once. You can look at your starting point, your destination, and all the winding paths in between. But when you are actually walking that path, you only experience one step at a time. Our experience of time might be that limited step-by-step journey. The broader view might be inaccessible to us, not because it does not exist, but because our brains and bodies are built to navigate three-dimensional space, not higher dimensional time. The most tantalizing part of this idea is how it shifts our understanding of what a moment even is. A moment might not be a singular point in time, but a slice of a larger temporal geometry. The universe might already contain every moment in its vast multi-dimensional tapestry, and what we call the present is simply the slice we are able to perceive, like a flashlight beam passing across a mural too large to see all at once. So when we think of time as linear, flowing, and unavoidable, we might be relying on an interpretation suited to our dimensional limitations. Time could be larger, thicker, more flexible, and our familiar timeline, the steady stream of moments that carries us from childhood to adulthood, from sunrise to sunset, is just the narrow channel carved out for three-dimensional beings. We live inside a single temporal thread, while the universe may contain a whole woven fabric of possibilities. If space can be deeper than it looks, then time certainly can too. And somewhere beyond our perception, time might stretch in directions we have never imagined, forming shapes we cannot see, holding connections we have not yet uncovered. We walk through our timeline one step at a time, but the universe may be standing outside the theater, holding the entire reel. If you have ever watched ants marching across a sidewalk, completely unaware that you are towering over them like a mildly curious skyscraper, you already have a tiny hint of how a higher dimensional being might look at us. To the ants, the sidewalk is the world. It stretches from the patch of grass on one side to the dropped French fry on the other. They navigate bumps and cracks with the seriousness of seasoned explorers. They have no idea that from your perspective, their entire world is a flat strip under your shoe, a place you could cover with one footstep if you were having a dramatic day. Now imagine that same relationship, but with us playing the ants and a higher dimensional observer playing the skyscraper. Except the gap between us and them makes the ant-to-human difference look like a rounding error. From a higher dimensional viewpoint, our universe might appear like a thin, delicate film, something with structure but lacking bulk compared to their realm. Think of a soap bubble shimmering in the sunlight. From your perspective, it is fragile, nearly weightless, and impossibly thin. Yet it contains swirling patterns and reflections that hint at a kind of internal beauty. To a being living in the higher dimensional air around that bubble, the bubble has form, shape, and behavior, but almost no depth. That might be exactly how our entire cosmos looks from a dimension beyond ours, intricate, shimmering, full of internal drama, but fundamentally sheet-like. If such a being could peer into our universe, they would not be peeking through space the way we do. They would be looking across our dimensional layer the way you look across a page of writing. Our galaxies, planets, and people would not float in three-dimensional space. They would cling to the surface of a higher dimensional structure, like specks of dust dancing on the skin of a soap film. To them, we might appear as patterns, rich, dynamic, complicated patterns, but patterns nonetheless, etched into a boundary they can survey with a glance. Now imagine how strange our movements would look to them. When we walk from one place to another, we feel like we are moving through deep, open space. But if our entire universe is just a thin sheet from their point of view, then our movement across space might look like little squiggles on a surface, maybe something akin to watching wrinkles ripple through fabric when you tug at it. Traveling across the galaxy, an endeavor that, for us, would require monumental technological leaps, might appear to them like a microscopic shuffle across a tiny patch of an unimaginably larger expanse. Our concept of direction would look oddly limited. We only know up, down, left, right, forward, backward. But to them, those directions might seem like extremely restricted motions, the way a pencil drawing looks unable to step off the page. If we moved up, they would see us moving only within the confines of our dimensional sheet. Meanwhile, they could lift themselves effortlessly into a direction we cannot even imagine, like a person taking a step away from a chalkboard drawing while the drawing remains forever stuck to the surface. Communication would be even stranger. The speed of light, which we treat as the universe's absolute speed limit, might appear laughably slow to a being not confined to our dimensional rules. It would be like watching someone deliver messages on horseback in a world full of smartphones. They would see our signals as ripples moving across a flat pond, while they themselves could send fully three-dimensional waves through a deep ocean. To them, our physics would look conservative, cautious, and needlessly constrained, like we have been handed a whole orchestra but insist on playing a single drum. But perhaps the most mind-bending aspect is how they might perceive our existence. To us, life unfolds moment by moment. But to a higher dimensional observer, our entire timeline, birth, growth, triumphs, mistakes, the moment you accidentally waved back at someone who was not waving at you, might be visible all at once. Not because they are time travelers, but because they can see across our dimensional sheet in ways that reveal its full structure. Just as you can see an entire photograph at a glance, they might see an entire lifetime as a complete shape, a kind of temporal sculpture stretched along the surface of our universe. That does not mean we would seem lifeless to them. Instead, we might appear dynamic in a new way, like watching a full animation all at once, rather than frame by frame. Our choices, movements, and interactions would form patterns that reveal structure we could never notice from inside the timeline. They would see not a sequence of events, but the whole interconnected form those events create. Even our most mysterious phenomena, things we struggle to explain because we cannot access extra dimensions, might be obvious to them. Think of how a two-dimensional being would react if a three-dimensional object passed through its world. Sudden appearances, baffling disappearances, shapes changing for no apparent reason. To us, that is higher dimensional weirdness. To them, it is Tuesday. And maybe most humbling of all, our concept of the universe would seem adorably small from their vantage point. What we call everything, the totality of space, time, matter, and energy, might look like a frontier outpost nestled on the surface of a much grander dimensional structure. We would be a membrane suspended in a richer space, the way a soap bubble floats inside a room without ever touching most of it. Yet even if we seem tiny, flat, and limited, there is beauty in that perspective, because from their point of view, our universe is a breathtaking pattern, a shimmering film full of complexity, motion, and meaning, a cosmic mural carved into the fabric of a higher dimensional reality. And every one of us is part of that pattern, a thread woven into the surface, contributing to the shape of something larger than we can possibly imagine. To a higher dimensional being, we are not small. We are intricate. And our universe is not thin. It is exquisite. If you tell a physicist that the universe might be a projection from a higher dimension, they will not pat you on the head and send you home. They will grab a notebook, 2 markers, 3 espressos, and say, "All right, let's see if the universe left any fingerprints." And that is exactly what many scientists are doing, combing through the cosmos like cosmic detectives looking for smudges, scratches, or odd quirks that hint our world might be the shadow of something deeper. It is not enough to propose the universe is a projection. Someone has to check for clues, like a detective poking around a crime scene where the only suspect is reality itself. One of the first places physicists look for whispers of the projection idea is the edge of the observable universe. Not because it is glamorous, though it is, in a giant cosmic horizon sort of way, but because the very farthest regions of space behave oddly. Imagine staring across a frozen lake and noticing 2 distant patches of ice that appear eerily identical, like the universe accidentally copy-pasted itself. Physicists have found some large-scale patterns in the sky that feel too coordinated, too synchronized, as if the universe ironed itself a little too neatly. If our universe were a projection, these patterns might be part of the underlying blueprint showing through, like seeing faint guides beneath the ink of a tattoo. The cosmic microwave background, the faint glow left over from the early universe, is one of the richest sources of potential hints. It is basically the universe's baby photo, grainy, slightly noisy, and yet filled with clues about how everything began. If the universe is a projection, physicists suspect that the patterns in this glow might reveal tiny imperfections, the same way a projector might leave subtle distortions on a screen that only show up when you look closely. These distortions would not be huge. They would be tiny, jittery fluctuations, like the universe breathing too quickly to hide it. Detecting them is tricky, though, because the cosmos does not like to hold still for a long exposure shot. Another big clue physicists search for is something called cosmic correlations. But do not worry, that is just a fancy term for stuff matching up in ways it probably should not. Imagine watching 1,000 people randomly throw confetti into the air. You would expect chaos. But if you look closer and notice that some of the confetti pieces keep drifting in nearly identical patterns, you might suspect there is an underlying rhythm or current shaping their motion. In the universe, when regions of space separated by impossible distances behave suspiciously alike, scientists raise an eyebrow, not a panicked eyebrow, more like the eyebrow of someone who definitely wants to check the attic to see if the house is haunted. Then there is the hunt for pixelation. If the universe is projected, it might have a smallest possible unit of length, like a cosmic pixel. Not a literal pixel you can see, of course. You would need a microscope so powerful it would be banned for making every object look unnecessarily judgmental. But if the fabric of space has a granular structure, like a mosaic made of unimaginably tiny tiles, it could betray its projected nature. Physicists look for these grains by studying high-energy particles from space, watching how they travel. If reality has pixels, those particles might jitter or blur in ways that reveal the underlying grid. Physicists also examine how cosmic information behaves, because if the universe really stores itself on a boundary, there should be rules about how much information fits into a chunk of space. It is a bit like checking whether a suitcase is actually empty or if someone secretly crammed it with sweaters. If the amount of information inside a region of space matches the amount that could theoretically fit on its surface, scientists take notice. It is the kind of match that makes theorists giggle uncontrollably before pretending they are calm and professional. Another place physicists search is in particle physics experiments, giant machines that smash particles together so violently that even the particles themselves would complain if they had filing rights. These collisions create tiny flashes of extreme conditions, miniature laboratories where space might reveal whether it is a projection. If space-time behaves differently when pushed to extreme densities or energies, it might hint at a deeper mechanism behind the scenes. Think of it like tapping a wall you suspect might be hollow. The sound it makes tells you something about what lies underneath. Even gravity gets dragged into the investigation. If gravity really arises from information rather than mass, as some theories propose, then there should be certain situations, tiny, precise, incredibly delicate situations, where gravity behaves just a little differently than expected. Physicists build sensitive instruments that measure gravitational effects with absurd precision, the kind of precision that would let them detect a fruit fly landing on a trampoline from several blocks away. If they ever spot an anomaly, even a tiny one, it could be a clue that gravity is doing more than just pulling. It is keeping track of cosmic data behind the scenes. Finally, there is the philosophical clue hunt. Scientists look for conceptual cracks in our understanding, places where the equations get tangled, where the rules contradict themselves, or where something just feels off, the way a painting might feel slightly wrong if one of the shadows does not match the light source. These cracks often point toward deeper truths. If the universe is a projection, some of these oddities might not be mistakes. They might be hints that our current view is incomplete, like reading only the footnotes of a larger story. The universe does not hand out answers easily. It tucks clues in distant galaxies, buries hints in subatomic behavior, hides secrets in faint cosmic light, and occasionally sprinkles mysteries into mathematics just to keep everyone entertained. And physicists, armed with telescopes, detectors, equations, caffeine, and boundless curiosity, follow these clues not because they expect a definite revelation, but because each hint deepens the mystery. We may never find a single glamorous piece of evidence that declares, "Congratulations, your universe is a projection." But every clue brings us closer to understanding the possibility, and the search itself, full of wonder, guessing, checking, and the occasional muttered complaint from someone analyzing data at 3 a.m, makes the universe feel bigger, stranger, and far more playful than we ever imagined. Trying to imagine a higher dimensional reality is a bit like asking your houseplant to picture the Louvre. It is not that the plant is unintelligent. It is just working with a completely different set of sensory tools. Likewise, our minds are wired for 3 dimensions and 1 timeline. Anything beyond that is like mental yoga. Possible, but you may end up in a position no one can describe. Still, speculation is part of our cosmic birthright, so let us stretch our imagination and ask, if our universe is just a projection, what could the real higher dimensional world be like? For starters, higher dimensional reality might not resemble space as we know it. We think in terms of here and there, near and far. But in a richer dimensional framework, location might be a negotiable concept. Instead of distances defined by straight paths or curved geographies, positions in higher dimensions could be defined by relationships or properties we cannot visualize, like proximity determined by similarity, resonance, or shared structural patterns. Imagine a place where 2 things are close, not because they sit beside each other, but because they share a particular signature or rhythm. Geography in such a realm could behave more like music than maps. And movement, that might be even stranger. In our universe, movement is a sequence of steps from one point to another. But a higher dimensional being might navigate reality the way a reader jumps between chapters or paragraphs, leaping across conceptual terrain instead of physical space. Travel might be less like walking down a road and more like shifting perspectives or rearranging oneself within an elaborate multidimensional framework. A simple shift in whatever counts as orientation in higher dimensions could reposition them in a way that, to us, would appear instantaneous and utterly impossible. Not teleportation, something more like reshelving themselves in a cosmic filing system. Even solidity could behave differently. Matter in our universe feels solid because particles organize themselves into structures with boundaries, but in higher dimensions, boundaries themselves might be flexible or dynamic. A higher dimensional object could appear to flow from shape to shape, not by deforming, but by revealing different slices of its full structure. Think of a sculpture with infinite hidden layers that can present new forms by rotating into directions we cannot perceive. To them, form might not be fixed. It could be a choice, a configuration selected from a larger catalog of possible cross-sections. A higher dimensional landscape might also support entirely different kinds of interactions. We are familiar with forces that push, pull, attract, or repel, but interactions in higher dimensions might not involve forces at all. They could operate through alignment, merging, or pattern matching. Entities might influence each other not by exerting pressure, but by adjusting aspects of their multidimensional structure. Imagine a conversation where instead of speaking words, you shift your internal geometry slightly, and someone else understands the meaning instantly. It would make communication suspiciously efficient, if also dangerously intimate. And what about life? If higher dimensional beings exist, their experience might be less tied to survival and more tied to coherence. Instead of worrying about energy, temperature, or resources, they might focus on maintaining the integrity of their multidimensional patterns. A disruption in their form might feel to them the way pain feels to us, not in a physical sense, but as a kind of disharmony within their structure. Their version of healing could involve reorganizing themselves, smoothing out distortions, or reintegrating lost pieces. It might be as natural to them as adjusting posture is to us. Their perception would likely leave ours in the dust. We detect the world through senses tuned to three-dimensional space, light waves, vibrations, chemical traces. But a higher dimensional being might sense entire relationships or configurations at once. They could see patterns that stretch across what we think of as vast cosmological distances, not because they have better eyesight, but because their perception functions in directions we do not possess. It would be like us watching a tiny two-dimensional drawing while being simultaneously aware of the entire sketchbook, every layer of the picture, and the intention of the artist. They might perceive not just what is happening, but why it is happening. Even their environment, if one can call it that, could be something beyond landscapes or structures. Instead of terrain made of mountains, fields, and oceans, their world might be composed of abstract entities, patterns, flows, gradients, or regions defined by stability versus flux. Picture a realm made not of objects, but of states. Some regions might feel calm and ordered. Others might feel turbulent and shifting, like weather systems made not of air, but of geometry itself. A higher dimensional forest might be a region where certain patterns cluster, while a higher dimensional storm might be a region where those patterns twist chaotically. Time in their world might not be a single unfolding sequence but a layered phenomenon. They might experience multiple kinds of time simultaneously, some flowing, some looping, some branching, some standing completely still. Their decisions might influence shapes in this multi-layered temporal architecture, allowing them to navigate consequences the same way we navigate a room. They might not experience time as a river, but as an ocean, where currents move in all directions. Perhaps the most mind-stretching idea is that their reality could contain symmetries and structures we cannot express mathematically with our current tools. Just as a circle is invisible to a creature confined to a line, there could be structures so foundational to higher dimensional existence that we simply lack the intellectual handles to describe them. Their cosmos might be rich with patterns more intricate than anything our physics has yet imagined. And in this higher dimensional expanse, our universe, our proud, sprawling, star-speckled universe, might appear as a small but beautiful phenomenon, a glowing membrane or film suspended in a much larger arena. Not insignificant but specialized, like a delicate artwork created by the dynamics of their world. From their perspective, our cosmos could be a single expression of a far broader reality, a dimensional bloom in a garden we cannot yet perceive. If the universe truly is a projection, then the higher dimensional realm is not just bigger, it is stranger, richer, and more layered than anything we have language for. But imagining it brings us closer to understanding that our world, for all its wonders, might be only one page in a much larger book. And speculation, fearless, joyful speculation, is how we begin reading the pages we cannot yet see. If, after all this exploring, investigating, imagining, and occasional head tilting, you find yourself staring at the ceiling and wondering whether your entire life is happening on the surface of some cosmic projection screen, take a breath. Not because the idea is scary, but because it is astonishing. It reframes everything, not by shrinking our importance, but by expanding the theater in which our existence plays out. If we truly inhabit a projected universe, an intricately woven shadow cast by a richer dimensional realm, then every moment we experience is part of a much grander story than we ever suspected. Think of it this way. We humans have always lived inside mysteries. Before telescopes, the night sky was a scattering of lights we told stories about. Before microscopes, life itself was a puzzle we could only guess at. The idea that our entire universe might be a projection is simply the next chapter of that tradition. It is the cosmos saying, "You have peeled back many layers. Here is another. Try this one on for size." Far from undermining our reality, the concept adds depth to it. It means our universe has structure beyond structure, meaning beyond meaning, like a painting whose beauty does not diminish when you discover the hidden embossing in its canvas. To live inside a possible projection is not to be fake. A shadow is not fake. A hologram is not fake. They are different expressions of something real. We too are expressions, patterns, forms, stories unfolding inside a universe that just might be the sculpted surface of a larger dimensional masterpiece. That does not make us less. It makes reality more. It means the universe chose a breathtakingly intricate way to exist, one that allows beings like us to emerge and wonder about it. And wonder is the key. Our species has a special relationship with curiosity. A bird can fly, a dolphin can navigate the ocean, but humans, well, we sit under the stars and ask them to explain themselves. We look at reality and immediately demand its backstory. If the universe is indeed projected, then we are the audience that stood up mid-performance and said, "Hold on, who built the projector?" That stubborn spark of curiosity is one of the most magical things about us. Living inside a projection also casts our day-to-day experiences in a new light. The sunrise painting the horizon in pinkish gold might be more than weather and optics. It could be a moment in the unfolding of a complex encoded pattern. The laughter of a friend could be one of the countless ways the projection allows consciousness to bloom. Every leaf, every breath, every choice you make could be part of the way the projection brings meaning into being. Instead of diminishing reality, this view elevates it, turning each moment into a tiny miracle of cosmic craftsmanship. There is also something profoundly comforting in the idea that our universe is shaped by deeper dimensions. It suggests that even when life feels chaotic or inexplicable, we are moving within a structure far wiser and more intricate than we can perceive. We may not understand the full architecture, but we are part of it, and that makes the chaos feel a little less lonely. It is like realizing you live inside a cathedral so vast you can only see the part lit by your lantern, yet knowing that the structure stretches far beyond, filled with arches and echoes and mysteries that give every footstep meaning. And what about purpose? If the universe is a projection, does that change how we think about our place in it? Perhaps. It might remind us that meaning is not handed to us from outside. It is something we create by exploring, connecting, and imagining. A projected universe is still a universe we get to shape through our choices. Our stories still matter. Our actions still ripple outward, and the connections we forge still influence the unfolding of our lives. Whether projected or not, we are still the authors of our own narrative threads. This perspective also brings humility, a gentle kind, the kind that says, "I am small in the cosmic scheme, but I am part of something extraordinary." Humility does not mean insignificance. It means appreciation, the ability to stand at the edge of the ocean or beneath a starlit sky and feel awe instead of fear. If we live inside a projection, the awe only grows. The ocean is not just waves. The stars are not just glowing spheres. They are pieces of a grand dimensional tapestry being expressed in our world. And you, yes, you, are woven into that same tapestry. There is a cinematic beauty to this idea. Imagine pulling the camera back at the end of a film. The shot widens from a single character to a landscape, to a planet, to a galaxy, and finally to the shimmering cosmic boundary on which the projection plays. The whole universe glows like a luminous mural, and every human story is brushed into it, with delicate strokes. You see how everything fits together, how everything belongs. We do not know if the projection idea is true, of course. The universe keeps its secrets close. But asking the question reshapes the way we see ourselves. It invites us to approach reality with curiosity, creativity, and a willingness to embrace mystery. It reminds us that even the most familiar parts of our world, a cup of tea, a conversation, a moment of silence, may be facets of a universe far more extraordinary than we can imagine. And at the end of it all, whether the universe is a projection or not, one truth remains: we are here, awake, thinking, wondering. We are creatures who look at existence and attempt to trace its origins in the dark. That quest for understanding is the real magic. The universe may be a projection, but our wonder is not.